Okay, so welcome to 4Keys Private Tuition. So we'll continue with our lessons on Equilibria. So we're going to proceed here, starting off with the ionic product of water, which we talked about in previous lessons. Here are some important points related to Kw that you must know. The value of Kw is the same in a solution at a given temperature. So the value of Kw remains the same for a specific temperature. Okay, so Kw has a value of 1,008 times 10 to the power negative 14 moles squared Tm negative 6. This value changes if the temperature changes. Okay, we need to know that pure water has an equal concentration of H plus and OH minus ions. And in other words, the concentration of H plus is equal to the concentration of OH minus ions. So we can simplify here our Kw as an expression. We can simplify it as an expression in terms of H plus only. Since H plus is equal to OH minus, we can have Kw is equal to H plus concentration of H plus squared. So you can use this. And what you can do is you can use another scale, which is the log scale, in which case you don't use Kw but you calculate pKw. So if you know the log scale is about powers of 10, so pKw is calculated from Kw and it is calculated using pKw is equal to the negative log of 10 Kw. So in other words, pKw is the power to which you must rise 10 in order to get your Kw. Only that in this case we have a negative sign here, so it's the negative power of 10. So Kw is equal to 10 to the power negative pKw. So you can find your Kw given pKw, or you can find your pKw given your Kw using negative log 10 Kw. So it's another scale which should be convenient for you. Kw uses smaller numbers, which are powers of 10. So this should be a convenient scale for you. So don't be intimidated by this pKw variable. It's simply supposed to make your numbers smaller, but you can interpret it the same as your Kw. It gives you the same information. Okay, let's move on. So pKw is used to display Kw values on a smaller scale, which makes it easier to use. Then pKa, so we looked at Ka before, so you can also use pKa, which is a much smaller scale. So pKa is another way of measuring the strength of an acid, similar to pH. We saw that when your Ka is high, your acid is stronger. When your Ka is low, your acid is weaker. So, but in this case now, it's the inverse of that. The lower the value of pKa, the stronger the acid. So this scale is the inverse of your previous scale, your Ka scale. So pKa is again equal to negative log 10 Ka. So these are negative powers of 10. pKa values are negative powers of 10, which will give us Ka values. So for example, calculate pKa values value from an acid with a Ka value of 7.52 times 10 to the power negative 3. So pKa is equal to your negative log base 10 here, Ka. So pKa is equal to, you substitute your 5 in your 7.52 times 10 to the power negative 3 here to get a pKa of 2.12. So you can see here, if you look at this number here, of course it's a smaller value compared to this. If we get mathematical here, we see that 7.52 times 10 to the power negative 3 is a smaller number compared to this one, right? However, this one is an easier number to work with. These are whole numbers, 2.12 compared to these numbers that are in standard form here. So the Ka scale here has been converted to pKa scale, and this should be convenient compared to this when it comes to interpretation. So you can again find your Ka value from this expression. So let's look at this. Calculate the pH of 0.0250 moles per cubic decimeter of ethanoic acid at that temperature which is a pKa value of 4.75 at 298. So the temperature is emphasized here. We're given the temperature value here and here. Okay, so how do we do that? Ka is equal to our 10 negative pKa, and which is 10 negative 4.75. That gives us a Ka value of 1.78 times 10 to the power negative 5 moles per cubic decimeter. Okay, so you should be comfortable moving from pKa to Ka. Okay, let's look at this one. This was the first part here. Okay, calculate the concentration of H plus ions from Ka expression. Now in this case, we have to express our Ka as equal to concentration of H plus squared over the concentration of the acid in this case. This is because this acid, when it dissociates, it will give you the conjugate base, which is the CH3COO minus ions, and H plus in equal concentrations. It's 1:1, so we can express our products in terms of H plus only, so it becomes H plus squared. So we can substitute values there and substitute our values here. If we're given our Ka, the K that we just calculated here, 1.78 times 10 to the power minus 5, which is this one, times the concentration of the acid here, which is 0. Calculate the pH of this, so that's the concentration of the acid, yes, so 0.0250, yes, and we end up with our concentration of H plus squared being equal to 4.45 times 10 to the power negative 7, and we can root here to find our concentration of H plus ions. And then lastly here, what we have to do is substitute that concentration of H plus ions into our negative log 10 for pH. You get 3.18. So let me just go through this again. The question was calculate the pH of 0.0250 moles per cubic decimeter of ethanoic acid at this temperature, and we were given the pKa value. So firstly, we have to find our Ka value from the pKa value by raising 10 to the power negative pKa, and we found 1.78 times 10 to the power negative 5. And secondly, we use our Ka to calculate the concentration of H plus, because we need concentration of H plus to determine pH. So concentration of H plus ions here, so we had to express our Ka in terms of H plus only and the acid here. And I say that this is because this one is a monoprotic acid. If you still remember, it will give you exactly 1 more of H plus ions and 1 more of CH3COO minus, the conjugate base here, in a proportion of 1:1. So every mole of the ethanoic acid will give you exactly 1 more of the conjugate base and 1 more of the H plus ion. So this is why we have to say here, the products can be expressed in terms of H plus only because they are 1:1, so H plus squared. So you need to understand what happened here, and we substitute the values that were given for Ka, or rather make this the substitute of formula. So we end up with this expression and substitute our Ka and our concentration of the acid, and we had to remove the square sign here, and we go to this stage. So you can practice calculating, making these calculations. Okay, let's move on. So we're going to be talking about buffers, which are an important part of our study. Okay, so let's just say here what a buffer is. A buffer is a chemical that resists change in pH when small amounts of acid or base are added. Okay, so you need to understand here that buffers do not stop the change, but they just resist. So there's going to be a change in pH. It's going to be small, it's going to be resisted. Okay, so there are 2 types of buffers, and we have an acidic buffer and a basic buffer. So let's look at acidic buffers. Acidic buffers resist the change in pH in order to keep the solution below a pH of 7. So we have a buffer solution whose pH is below 7, and it resists changes in pH such that the pH remains below 7. Then this is an acidic buffer. It has a pH below 7. So it is made from a weak acid and a salt of its conjugate base. So you need the weak acid and the salt of its conjugate base. Okay, or rather what you can just say is that you need a weak acid and its salt. Okay, it's just the same, a weak acid and its salt. If you want to be more specific, a weak acid and the salt of its conjugate base. If you remember in the previous video, we talked about conjugate acids and bases. You need to go back to that. If you don't know how to identify a conjugate acid and its conjugate base, then you need to go back there. But here, our CH3COOH will dissociate to give us the conjugate base, which is CH3COO minus plus our H plus ions. So the CH3COO minus, this part here, this is our conjugate base. Now when it combines with sodium, in this case, that's the salt. So you need this combination, the acid, weak acid, and its salt, or the salt of its conjugate base. This is what makes you the acidic buffer in this case. So we have two equilibrium reactions that take place in every buffer. In every buffer solution, there are going to be two equilibrium reactions happening at the same time. So the first one in this example would be your acid, which dissociates to this conjugate base, and your H plus ions. Remember what we said about weak acids, they dissociate weakly, so the equilibrium lies well over to the left. So there's going to be a high concentration of this and a low concentration of these two products. Because it's a weak acid, the equilibrium lies to this side. So there's going to be a large proportion of those acid molecules that are not dissociated. Okay, and then the second equilibrium that's going to exist there is that of the salt. So the salt is going to fully dissociate. So the salt fully dissociates to give you the conjugate what? What is this? The conjugate base of the acid, and of course these ions. So you're going to have a high concentration of these of the conjugate base, and also a high concentration of the sodium ions in this case. So these are the two equilibria that you're going to find in every buffer solution. So we need to understand how then the buffer resists changes in pH. So for this acidic buffer, I said it has to keep its pH below 7. So what happens when you add an acid? When you add an acid, the pH must fall. Must fall downwards. 7,654 must go down all the way to 0. But what really happens now when you add an acid to a buffer such as this? So the H plus ions are going to be taken out of solution. The H plus ions that you add, they will quickly react with the conjugate base ions. This is the conjugate base, which are in solution. So you have a large proportion of this these conjugate base ions that are coming from the salt here. So this will immediately react with the added H plus ions. And what does this result in? There is a high concentration of this from the salt, like I said, and it's going to result in your equilibrium shifting to the left. So you are going to have those extra H plus ions being removed to make more of this. So the equilibrium is going to move in this direction, forming more of the acid. Okay. And what happens when you add a base, which are OH minus ions, to this buffer? So these ones are going to react. The OH ions will react with the H plus ions. These are the H plus ions. But remember, we have a low concentration here. However, these can be replenished, or they can be replaced from this equilibrium, where the forward reaction, once you remove these H plus ions, then this equilibrium is going to provide more, since you have a high concentration of this acid. So it's going to replace those that you remove according to Le-Chatelier's principle. So this is what happens. And in doing so, we remove those OH minus ions from our solution. So this is how the buffer resists when you add an acid or when you add a base. Right, let's move on. So like I said here, the equilibrium is going to shift to the right to replace the H plus ions that react with your OH minus ions if you add a base. Okay, So this is just something for you to know that acidic buffers can also be made from an excess of a weak acid and a strong base. So let's see what happens. In this case, we have your ethanoic acid, which is a weak acid, and but you need an excess of the weak acid. Take note, an excess of the weak acid and a strong base. So what happens when you have an excess of a weak acid and a strong base? So all of the base reacts with the acid in the following way. So all the base, this strong base, is going to react in this manner to give this conjugate conjugate base of the acid and water. Okay, but we have an excess of the acid, so some acid molecules are still going to react even after all the base has reacted with some of the acid molecules. We are still going to have extra acid molecules remaining. So that means we have another equilibrium that is still taking place in this solution, which is this one, because remember you had an excess of the weak acid, so the remainder of the weak acid can still have this equilibrium, whilst you also have this equilibrium in your solution. So you end up with a buffer solution. Let's talk about basic buffers. So what is a basic buffer? It resists change in pH in order to keep the solution pH above 7. They are made from a weak base and its salt. An example of a weak base, we have ammonia, and its salt is ammonium chloride. So when you mix these two, you're going to have two equilibrium reactions taking place. So your ammonia with water will give this one, the ammonium ions and OH minus ions. But remember, this is a weak base, so it's not going to fully dissociate this one. So you're going to have a low concentration of the ammonium and a low concentration of the water, and a high concentration of the weak base. But now for the salt, it's going to fully dissociate, so it will give you a high concentration of the ammonium ions and a high concentration and a low concentration of the salt. So you now have those two systems at the same time. So what happens when you add a base to this buffer? So the OH ions are going to react with the ammonium ions, and there's a high concentration of these from the salt to form more of the NH3 and H2O. So we're going to have this reaction shifting to the left. We're going to form more of the NH3 and H2O. But what happens now when you add an acid? An acid is going to react with so the H plus ions will react with the OH minus ions, these ones, and of course there's a low concentration of these, but every time they react, they are going to be replaced, so causing this equilibrium to shift to the right. So they're going to be replaced because we have a high concentration of this weak base to replace those OH minus ions. So this is what happens according to Le-Chatelain's principle if you remove these ones, even though there's a small concentration of these ones. So that's how a basic buffer will act. So that reaction will shift to the right. So you need to understand these principles. Now let's talk about titration curves and buffers. So when you are carrying out the titration, there is a stage where a buffer is created. So let's look at this. So initially, when you add, so in this case we're adding a base to an acid. So there is plenty of OH minus ions from the strong base that react with the H plus ions from the weak acid. So this is a strong base weak acid titration. But there's a stage where the pH now changes slowly. This is where we have our buffer system formed. So the curve then becomes more level. A buffer solution exists between the weak acid and the salt of the conjugate base. So this resists the changes in pH. Remember what we said, you would need, if it's an acidic buffer, you need a weak acid and the salt of its conjugate base. So this is what you have in this titration curves. So I'll meet you in the next lesson where we're going to be talking about okay, so we said we'll talk about uses of buffers. There are many uses, and one of the common example is that your blood itself is a buffer. So you can look at other uses where you need solutions that would resist changes in pH. You can do that on your own. Let's move to calculating pH of a buffer. You must know this, definitely know this. So to calculate the pH of a buffer, you need to know the Ka value, the acid dissociation constant value, and the concentration of the weak acid and its salt. Okay, so you need, for example, here, calculate the pH of a buffer that contains 2.35 times 10 to the power minus 2 moles of methanoic acid. So the moles of the methanoic acid are given here. 1.84 times 10 to the power negative 2 moles of the sodium methanoate. What is this? The salt of acid in a 1 cubic decimeter solution. The value of Ka here at 25 degrees Celsius for methanoic acid is, so this is the acid dissociation constant, is 1.78 times 10 to the power negative 4 moles per cubic decimeter. So let's see how you can go about that calculation. So firstly, write the equation and the Ka expression. So the equation for this acid, it dissociates to form this your conjugate base and the H plus ions. So your Ka is supposed to look like this. All right, but remember what we said here earlier on. We said that you can express Ka in terms of H plus only, in which case this is because we are saying here your acid, 1 mole of the acid will give you 1 mole of H plus and 1 mole of the conjugate base. However, for buffers, remember you're mixing an acid with the salt of its conjugate base. So you have another source for these ones. These ones are not coming from your acid. Remember, acid actually produces a few of these because it's a weak acid. So where is this coming from? The salt, the conjugate base, where is it coming from? This is coming from the salt of the weak acid. So we can't say the concentration of H plus is equal to the concentration of these, because these ones are coming from an external source from somewhere else. Okay, so this one is no longer valid. You can't do this. You must use the concentrations that you're given. Okay, because we are actually adding here the methanoic acid, as you can see, with something else, which is 1.84 times 10 to the power negative 2 moles of the sodium methanoate. So this sodium methanoate is providing for you this part. The large proportion of this is coming from the sodium methanoate. In fact, the proportion that comes from the dissociation of the acid is negligible. So we actually have to ignore that. This is what we're saying here. Not, we assume salts dissociate fully and weak acids dissociate poorly. Therefore, the concentration of the salt is equal to the concentration of the conjugate base. In other words, the conjugate base ions, all of them are coming from the salt. And the concentration of the acid at start is equal to the concentration of the acid at equilibrium. So we are assuming that the acid does not even dissociate here. The dissociation is negligible, such that the concentrations at start and at equilibrium are almost equal. So just note that the concentration of the salt is equal to the concentration of the conjugate base of that acid. Okay, so let's now put this into action. So rearrange the expression to calculate your H plus, the concentration of H plus, and here we are given the number of moles, and our concentration is given as concentration is equal to moles divided by volume. So we have to divide by 1. Fortunately, it's a 1 here. But however, there's also what we call the moles method. If you know all these are put into the same solution with the same volume, then you can just plug in the moles directly. So that would be your moles method. You can put in the moles and not the actual concentrations if you know that the volume is the same. Okay, the volume of the container is the same. Okay, so let's do this. So now let's add what we are given. So we are saying our Ka value here was 1.78 times 10 to the power minus 4, here it is, and our we're going to multiply here by the concentration of the acid at start. So by the concentration here of the acid, the conjugate base rather, which is 1.84 times 10 to the power negative 2. So this is remember, all the conjugate base ions are coming from the salt, so we just plug in the concentration of the salt. Okay, so this now, when simplified, gives us the concentration of our H plus ions. And then lastly, what we have to do is substitute in our negative log H plus, and we get a pH of 3.64. So just remember these assumptions here. So you can also see this simplified to This can be written as concentration of acid over concentration of salt. So don't be surprised when you see that this one is the concentration of the acid over the concentration of the salt. So it can be simplified that way. Okay, let's see what else we have. So in the next lesson, we'll talk about the solubility product. So make sure you join us. You tell a friend to come and join us at 4 Keys Private Tuition, where we have these online lessons, and we are going to be looking at past exam questions as well. So I'll see you in the next lesson.